All right. Thank you for sticking around this long. I know it's pretty late, so I'm going to keep it pretty light. So I'm Dani. I'm going to present to you today our new Solidity compiler called Solar. So a bit about me. As a background, I started programming actually in smart contracts in 2021. So at the time, there was no Foundry. The best toolkit that we had at the time was Hardhat, and we had a lot of problems. At least some smart contract developers had problems with the fact that testing was pretty slow and the iteration loop was slow, or other things made it hard to develop smart contracts by using Hardhat because of the separation of the languages used in production, Solidity, and the testing language using JavaScript. So at the time, this is the only thing we had, but we had these problems. So Foundry came out. When Foundry came out, I would say that it improved 100 times the DevX, at least for some people. This might be maybe too big of a number, but makes for a good slide. So as you can see here, this is the GIF we have on the README, just running force tests on Solidity, taking, well, like a second to run 1,000 tests or how many. So this was a massive improvement, at least for me at the time when I was just doing smart contracts. This is kind of like Foundry setting the bar higher for everyone else. So I was really amazed by this at the time. So I decided to look into how it actually works and why is it so much faster. How do we actually have Solidity tests in the first place? Like, how does that work? So I started looking into the actual code base, the libraries that it uses, and started contributing to it. And eventually, I managed to join the team. So I'm part of the Foundry team, more broadly, the open source team that is currently at Tempo. We maintain Reth, Foundry, and of course, our new project that I'm going to talk about later, Solar. So as Foundry got more adoption, and Foundry being kind of the leading toolkit used in smart contract development in terms of performance, we started to get more and more projects using it, of course, but also meant that existing projects became larger and existing test suites became larger as more complex contracts need more complex tests to test them, etc. So what happens is that as more Solidity code is being written, we're kind of like testing one part of the Solidity compiler that we never really had to worry about because the contracts that were developed initially, for example, think in 2015, we didn't even have ERC20. They were like simple, super simple one-file contracts that never really got to exercise the performance and other characteristics of the Solidity compiler. So as projects became more complex and bigger, we started to get complaints in Foundry that, hey, my project is taking 1 minute, 2 minutes to compile from scratch, and when I add a console log to, say, start like debugging a failing test, I have to wait like a minute to recompile the project. So this is something that was never really an issue at the beginning, but as Foundry became got more adoption, we started getting these complaints, and so this is kind of like a newer thing with Solidity that was never really thought of before. Another thing, of course, is the infamous stack to deep error. You've heard it the entire day. There's many fixes now and in the future, but this is another thing that was just never exercised because the contracts were never really that complex, and especially the tests being in a different language, you never had to write large Solidity files in the first place. So as we started to tackle these issues, we implemented some workarounds. For example, at the Foundry level, we implemented smarter caching. requesting less stuff from the compiler that we never, that maybe don't use by default. For example, requesting IR output in the JSON output from the compiler. We never really used it. So just by trimming the amount of stuff we request from the compiler, we got 5-star compile times. But these are really just like not temporary workarounds, but they don't really tackle the core issue itself. Another workaround is dynamic linking that I want to highlight really quick. This is a feature that we implemented recently in Foundry where, for example, decouples tests from source files, leading to potentially 100x speedups in compilation times. This is part of the blog post we released about this. So these are many workarounds, but they don't really tackle the core issue of the compiler itself having these performance issues. So what we developed, started developing internally, of course, dynamic linking is implemented using this tool. So what is this tool? It's Solar. We released Solar actually a year ago. Since then, we've implemented more features into it and also integrated more in Foundry itself. One of the features, of course, being the dynamic test linking I just described. What is Solar? So Solar is our new Solidity compiler. This is a compiler. This is not Sol-C. This is a separate binary that we develop ourselves. This is written entirely from scratch in Rust, from the ground up, with performance in mind, of course, tackling these issues that I just described. So the way we do this is, here's a few small points, but for example, data-oriented design, where we encode the performance into our data structure. So for example, the whole compiler is structured around multiple levels of IR instead of a single monolithic AST, for example, that this lets us implement smaller functions and lets us be able to operate on these multiple IRs in parallel, whereas in Sol-C, for example, everything is done on a single data structure that is mutated and iterated upon sequentially. Just this fact alone, being able to multi-thread the compiler, lets us get serious speedups. But of course, the whole structure of the compiler is designed with performance in mind. So, for example, also in the future, we will also be able to implement incremental compilation, where calling compiler multiple times, not even caching at the Foundry level, but directly at the Solar level, at the compiler level, where computation can be reused from previous attempts. Another design principle that we focus at Solar is, of course, library usage. So being developed internally and used in Foundry, we focus a lot on making the API pretty ergonomic and improving on the existing APIs that we had before, other libraries, and maybe also Sol-C as well, in terms of higher level operations, for example, iterating on the AST, as in traversing the actual source code of a file, or having just utility methods on common operations that you might need when interacting with the AST and stuff like that. Essentially, what we had in Foundry before was just a bunch of different libraries. For example, Solang, which is, I don't know if it's still maintained, but it's a Solana Solidity implementation that is separate from Sol-C. We used this library because it was written in Rust and it was just available. But of course, being for Solana, they had like different goals. Like we had to make many workarounds to even support to add support for it in Foundry. And for example, in Chisel, what we had was we were essentially re-implementing a compiler ourselves for the higher level operations that we needed in Chisel, for example, to inspect an expression. Like we would need to, given like a text input from the user in a REPL, we would need to parse it and then add it into the context and check, okay, is this an expression? What does this refer to? How do we display the type of it? And all of these things are essentially, we were just like re-implementing a compiler ourselves in Foundry. So we had this in many different places, in Forge FMT, in Forge Doc. So all of these different implementations of the Solidity AST and these higher level operations, we, of course, bundle them together and put them in Solar as a easier way to interact with. So we're not the only users of Solar. I've heard from many people using Solar, either AST parsing or even the higher level, or sorry, the lower level, more complete and analyzed IR called HIR. People using these for building static analysis tools. Of course, we use it ourselves in ForgeLint now. So yeah, the main point here is that like we focus a lot on library usage. If you're using it as a library and you have any feedback, feel free to contact me or open an issue on GitHub. So yeah, this is like an example usage from one of our examples of how you can use it in Rust as a library. This just simply parses a single file and then just prints it to the console using the debug format. Of course, focusing on performance, I have a few numbers here, 5 to 10x parsing. This is comparing against Sol-C using the CLI. This is single-threaded performance on parsing. We also do parsing in parallel, so given 100 files, all those 100 files will be able to be parsed in parallel. So numbers may vary there, but just the single-thread performance, we've been able to achieve 5 to 10x faster parsing. We also implement ABI output. So after parsing, we analyze a bit the contract. We figure out the structure of a contract, and then we are able to emit the same exact ABI format, the JSON format that you all probably know, 50x faster. So this is, again, like most of the structure of the compiler is done in parallel, so the numbers may vary from a large project being 50x faster or a super simple project being 5x faster, but we're generally seeing very large speedups all across the board. So for bytecode, we don't have that implemented yet, but we also expect similar numbers here in terms of both like compiler performance, as in time spent in the compiler, and also performance of the generated bytecode itself. This is a graph of the benchmark that we maintain. We maintain a set of benchmark programs that we test against a bunch of different implementations. Solar here being the green bar, and higher is better. You can see here the few different implementations. Slang, as maintained by, I believe, the Atomic Foundation. Sol-C, Solang, the one I just mentioned, the Solana implementation, and also Tree-Sitter, which is, I think, used by a couple of VS Code extensions or something like that for like syntax highlighting, and also the GitHub syntax highlighting for Solidity. This is another CLI benchmark. I'm just testing here the Solar ABI versus the Sol-C ABI for a simple, for Solidity. So I'm just passing the exact same arguments, just differing in how we actually pass the ABI argument. We're passing every file for source and test files. And we can see here 40 to 50x faster on my MacBook. So yeah, I mentioned before ForgeLint. This is powered by Solar. We were able to build this relatively quickly, as Solar is also inspired by the Rust compiler, which, as you may or may not know, the Rust compiler is renowned for its good diagnostics and, as in the errors and the warnings display, but also the way that it's actually implemented. It makes it very easy for someone to contribute a new lint or a new static analysis check in the compiler itself. So we took this inspiration from the Rust compiler and also implemented it in Solar. What's coming up next? Directly, in the next few months, we're already working on the LSP. This is the language server protocol, essentially just a command on Forge or Solar that spawns a server. And then, for example, a VS Code extension can use this server to query the state of your project, implement various functionalities like go to definition. When you click on a variable, it takes you to the definition or stuff like that. Another thing is, of course, the diagnostics, the same ones that you get in Solar in the CLI. You can have them in your editor, etc. After this, we're also, of course, planning also to finish the compiler itself. So this means implementing a backend. So right now, Solar is only a front end, which means it can parse and analyze code, but it cannot emit bytecode yet. We're looking into various different backends and ways to actually implement this. Of course, you've heard from many people today about bytecode generation and even Solidity themselves with the Sol core. So we're actively looking into how to hook into either an existing implementation or even implement it ourselves. So this is something that's up next for Solar. Yeah, this is all I have for you. If you have any questions, feel free to ask or DM me later. Thank you.
Amazing. Thank you so much, Dani. Does multiple backend near you plan to multiple backend? I think there might be something wrong with this question. Maybe I can.
Maybe you can decipher it.
I'm trying. How much has Solar improved the performance of the Forge formatter?
We didn't actively test the formatter since it was already OK, but I think it's probably 10 to 20x faster based on like also the previous benchmarks on Solang. So this graph applies directly to Forge FMT, since FMT only needs to parse the source code, and then it just basically goes over the AST and then like outputs a pretty printed version. So yeah, looking probably at 5-10x faster on a decently sized project.
OK. Since it's still work in progress, what are the current considerations for backends? For example, do you consider creating an EVM LLVM target?
That is totally possible. Everything is still on the table. Like we know about, for example, Yule. We can target Venom from the Viper team, or even Solex, as presented earlier, for an LLVM backend. So I think this is in the future going to be relatively straightforward to implement a conversion path between our internal IR and someone else's that also implements CodeGen. And yeah, this is one of the things that we're looking into.
That makes sense. Are there equivalence tests between Solar and SolC?
Tests, I'm not sure what that refers to. I guess, like, since we don't produce bytecode, we cannot test that, but our goal is to essentially have equivalent like semantics. So essentially, like compiling your code with SolC and compiling your code with Solar should be able to have the same semantics since we're implementing the same language. For ABI that we already have right now is 100% equivalent, yeah.
People are also asking when backend.
When backend, well, I can't give a date. It's a very kind of complex thing still, but I would say, I think end of Q1 we have at least a prototype ready next year.
Okay. And then, okay. So we have another spicy question, obviously.
Okay.
How does core versus classes solidity affect Solar?
Well, since Core recently came out, I don't think we had many opinions on it before since we never looked into it. But I think as of right now, it's still a prototype, so we're not actively looking into implementing it. But if it's something that's eventually going to be like a Solidity 1.0 kind of thing, yeah, then we're probably going to end up implementing it and just having the same goals in mind as a library usage and for performance.
Amazing. How was the relative parse performance measured?
It was measured as a, I believe, as a micro benchmark, as in you take a single file. For example, here, these are just single files of projects squashed into a single file, so flattened. For example, well, Counter and VM are single files, but Optimism, Solidity, these are larger projects squashed into one file and then just passed to the actual implementation. So for example, for Solang, Tree-Sitter, these are libraries, so we just call the main parsing function, and for SolC, we just pass it through the CLI as standard input.
And then in the end, you have a kudos. We love a well-performing parser. Job well done.
Thank you.
Thank you so much, Dani, for that final talk. Okay, we have one final question.
Oh.
Gonna quickly run with the mic.
Sorry, I actually tried writing it, and it was too long for the field.
Okay.
It actually relates to the question that has a typo. And so I'm going to read it without the typo. So does multiple backend mean you plan to support compiling Solidity code to non-EVM chains?
That is possible, yes, with more effort for sure. But yeah, the possibility is definitely there. For example, as we all know, like the RISC-V efforts for the next EVM implementation. That's definitely possible. The same as Yule implementing a different backend, we can also do the same, yeah.
And now for my question. So contracts need to run on-chain, so they need to be compiled to EVM, obviously. But tests, they are never intended to run on-chain.
Right.
So maybe are there plans to compile tests to x86 or ARM64 and not have to play around stack too deep when you're just writing a test?
Right.
And it doesn't make sense.
Yeah, that makes sense. We haven't discussed this, but that's definitely an interesting possibility. What we looked into before is compiling jitting bytecode, right? In a node, for example, where you have a very hot contract that is called millions of times, you can, instead of interpreting it every time, you compile it once at the beginning when your node starts up, and then you just execute the native code, which is much faster. And I'm sure this will be much easier when you have the full source code available, of course, for the contract. The tricky thing there is making sure that the semantics are the same. You basically have to re-implement the EVM stack natively. And I don't really know if that's a good thing to do for tests, since I'm sure they run already pretty fast, since it's just everything is done in memory in the EVM. But yeah, that's definitely a possibility.
Awesome. That will be it. Thank you.